Okay, let's do some examples here with this. Um, the first one I want to look at is this one with sines and some cosines in there, and we're going to use the sandwich theorem, but we won't explicitly use the sandwich theorem. Let's write down this limit. I'm going to go x to infinity. I'm going to take the, let's go 3 cosine of 2x minus 2 sine of x cosine of x. And then we're going to divide that by, let's just divide it by x squared plus 1. Okay, so I said we're going to use the sandwich theorem, and the top looks like it's going to do all kinds of funky stuff, right? It's the sines and cosines, so it's going to go up and down and all over the place. But the top never gets bigger than, say, 5, because the sine and the cosine never get bigger than 1, right? So this bit never gets bigger than 3. I'm going to subtract off something, but this bit never gets smaller than negative 1. So in absolute value, that numerator, if this turned out to be negative 1 and this turned out to be positive 1 at the same time, which it probably doesn't, but this will never be bigger than 5 on the top, right? And it's never going to be smaller than negative 5. Right? If I try and put negative 5 up there, it would never be smaller than negative 5. And then let's put our limit in. Try to anyway. Okay, so that's why I said it's using the sandwich theorem, because I can bound the numerator. I can bound the numerator between 5 and negative 5. And this, then, this looks like a constant value divided by something that gets really, really, really big as x gets big, right? So this is going to go to 0. This is also going to go to 0. And so this thing in the middle has to go to 0. And you should probably learn how to spell sandwich, huh? Still doesn't look right, but there we go. Sandwich theorem. Okay, so that's going to go to 0 because we can bound the numerator, we can bound the denominator, and go from there. Okay, let's do another one. Let's look at the limit as x goes to infinity. We're going to take 3x squared plus 2x minus 1. We're going to divide that by 2x squared plus x minus 3. Okay, so both the numerator and the denominator are polynomials of the same degree, and that means that I'm going to try and divide by the thing that's growing the fastest in either the numerator or the denominator. So I'm going to look at all of the terms around, and of all of the terms around, the x squared terms grow the fastest, right? So I don't really worry about the coefficients much, but this x squared is the thing that's going to be the fastest growing as x gets big. If there was an x to the fifth, it'd be x to the fifth that grows fastest. If it's sort of a square root function, it'd still be x squared, because x squared gets towards infinity faster than the square root. Exponentials, I'd be looking at exponentials growing faster than any polynomial, and that sort of thing. So let's see what I do here. As we get close to infinity, I said I was going to divide by the fastest growing thing. So every term is going to get divided by x squared. 3x squared over x squared plus 2x over x squared minus 1 over x squared divided by 2x over x squared, 2x squared over x squared plus x over x squared minus 3 over x squared. Okay, here the x squareds cancel, right? X squared cancels with x squared cancels with x squared. I'd be able to cancel this one with one of those, that one with one of those, and that's all that we can cancel. So this looks like the limit as x goes to infinity of a 3 plus 2 over x minus 1 over x squared divided by 2 plus 1 over x minus 3 over x squared. Okay. Each of these little bits in here, this one, that goes to 0, right? 2 constant value divided by something that gets really, really big goes to 0. That fraction goes to 0. This fraction goes to 0. This goes to 0. This goes to 0. Right? All those go to 0. And all I'm left with is 3/2. Okay. Maybe from algebra, sometimes you remember if you have two same degree polynomials, to find the horizontal asymptote, you take the leading coefficients and divide them by one another. Well, that's true, but why it's true is kind of this algebra that we just did here. Okay, let's try another one. Let's look at, well, in the last video we found an oblique asymptote. Let's do another oblique asymptote. Let's find the limit as x goes to infinity of x squared plus x plus 1 over x minus 1. That looks pretty similar to the one that we just did in the last video where we found an oblique asymptote. But what is the actual limit here? Well, I get to do the same thing. I want to divide by the biggest growing term anywhere, which in this case is x squared again. So if I divide everything by x squared, I have a 1 plus a 1 over x plus a 1 over x squared. And then in the denominator, I have a 1 over x minus a 1 over x squared. Well, the denominator, this goes to 0. The numerator, this goes to, it goes to 1. So this thing looks like it's going to go to 1 divided by 0. And so this is either going to go to positive infinity or negative infinity. And to figure that out, what we can do is we can figure out, okay, is it a positive value or a negative value as I get bigger and bigger numbers? So if I plug in really big x values, this is going to be positive. This is also going to be positive. So this is going to tell me that this is going towards positive infinity that way. Okay. And if you recall, our oblique asymptote, I think, was x plus 2, and we had the graph, it goes off towards positive infinity as I get close to infinity with the x values. Okay, let's see another one. Let's look at one like limit as x goes to infinity, say x squared plus 2x minus 7, and then I've got x to the 4th minus 3x cubed plus 2x squared plus x minus 2. Okay. So here, what's the biggest thing? Well, this x to the 4th is the biggest thing. I'm going to divide all the terms by x to the 4th. I won't have taken a limit yet, so I keep that limit written down. I've got a x squared, x to the 2nd over x to the 4th is a 1 over x squared, plus a 2 over x cubed, minus 7 over x to the 4th. Then my denominator, that turns into a 1, a minus 3 over x, 2 over x squared, and a 1 over x cubed, and a minus 2 over x to the 4th. Goes to 0, 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 goes to 0. This looks like the limit goes to 0 over 1, which is 0. Right, 0 over 1, we can actually do that division, so this is 0. If the degree of the numerator is smaller than the degree of the denominator, you're going to end up with a 0 for these polynomials. Let's do one that's not polynomial with this type of thing. So let's say I've got the limit as x goes to infinity. Let's say we have a 3 e to the x. I've got a plus e to the 2x. I've got 2 e to the 2x, and I've got a minus 2 e to the x. Okay, which of these terms grows fastest? Well, this exponential is going to grow faster than the e to the x one, right? So let's divide everything by e to the 2x. So this is limit as x goes to infinity. I've got 3 e to the x over e to the 2x plus, well, if I'm going to divide e to the 2x by e to the 2x, that's going to go to 1. And then in the denominator, e to the 2x divided by e to the 2x is going to cancel, and I'm going to be left with a 2 there, and then I'm going to have a minus e to the x over e to the 2x. Okay, we said that the denominator grows faster than the numerator, and so because we've done that, we've taken the thing that grows bigger. The fraction is going to have a much bigger denominator in the long run than the numerator is. So this is going to go to 0, and this is going to go to 0, and I'm going to be left with 1 over 2. So that's going to go to 1/2. So at this point, I should probably talk a little bit about how these things are compared, maybe sort of heuristically. So let's sort of write down things that grow slow to things that grow fast. So slow on this side, fast on this side. Logarithms are the slowest growing function that we kind of regularly see. And then we've got roots. And then we've got polynomials in the middle. And based on degree, right? Degree 0 doesn't grow at all. And then degree n, degree n plus 1, and so on. So they're going to grow faster in terms of degree. And then after polynomials, we get exponentials. Okay, so logs grow the slowest, and then roots, and then polynomials, and then exponentials. That's kind of the order of how fast things are growing, slow to fast, that way through these different types of functions that we have. So these guys, I would call these guys algebraic, and you're going to have low degree here, and then high degree here. But all your algebraic stuff comes in the middle, logs are on the left, exponentials are on the right. So for example, if I had like an x to the 7/3 compared to x to the 9/5. Okay. This has degree 2 1/3. This has degree 1 4/5. Right. So this is going to be faster since its degree in some sense is higher. I don't want that low degree to be associated to that. Low degree is that one, high degree is that one, right? Okay, so this is the faster growing one. So if you had something in a fraction, limit x goes to infinity, maybe I have an x to the 7/3 plus x to the 9/5 divided by 2x to the 7/3 minus 3x to the 9/5. The thing that I would divide everything by is the one with the bigger degree, so we divide by x to the 7/3 in all of these, and everything would cancel except for the 1/2. This would go to 1/2. Sort of, you look at the leading terms again, but the leading terms are based on how fast things are growing. Let's do, say, another one with this idea, just one more. Say limit x goes to infinity. Say I've got the log of x plus the log of x divided by, say, the square root of x plus log of square root of x. Okay, which thing grows the fastest here? The square root of x. Okay, so of all of these terms, this thing's going to grow the fastest. If I divide everything by a square root of x, I'll have log over square root of x plus log of x over square root of x divided by square root of x over square root of x, which is equal to 1, plus log square root of x over square root of x. I haven't taken a limit yet, so I should write that in there. And this is going to go to 0 because the denominator grows faster. This goes to 0 because the denominator goes faster. This goes to 1. And this goes to 0 because the denominator goes faster. This looks like 0 over 1, which is 0. Okay. 2 more, and then we'll call it good. The limit of the arctangent. Oops. The limit of the arctangent as x goes to infinity. So the arctangent says, if I get, what angle am I getting close to if the ratios are getting close to infinity, right? So in a trig picture here, the ratio for the tangent is the opposite over the adjacent, y divided by x, right? And I want to get this close to infinity. As I get closer and closer up here, as my triangles get closer and closer to just being right on the y-axis, this y value divided by this x value, that ratio gets really big, right? Right now it's maybe 3 to 1. Here it's going to be like 10 to 1 because this x value is really small. This guy's really, really tall compared to this. It's probably 10 times as tall as it is wide. As I get close to infinity, that means that my angle is getting close to 90 degrees, which is pi over 2. Okay, and if I go towards negative infinity, the arctangent of x, well, that means that the ratio is negative. I'm getting close to negative pi over 2 because I want to be in quadrant 4 with those. So those are two that are fairly common trig limits that will come up and are really pretty useful in some calculus stuff that we're going to do either later this semester or when you get to Calc 2. Okay, the last type of problem that I want to do is one of these where we have to kind of rationalize denominators, rationalize numerators. We've done that with some limits in the past. Well, we kind of get to do that, but we're not going to have actually fractions. We're just going to kind of rationalize some expressions. So I want the limit as x goes to infinity. Let's try this one. Let's take the square root of x plus 16 minus the square root of x plus 25. And we're going to try and find that limit. Well, it'd be nice if I didn't have square roots, because basically right now it looks like, well, this goes to infinity and this goes to infinity, so this is infinity minus infinity. Well, infinity minus infinity, depending on how close together those things are, could be finite. It might be positive infinity, it might be negative infinity, we don't know. So we're going to rationalize this. And to do that, we're going to multiply kind of by the conjugate deal again. So this is the limit as x goes to infinity. I've got the square root of x plus 16 minus the square root of x plus 25. We're going to multiply that by the square root of x plus 16 minus the square root of x plus 25. Plus the conjugate bit. Okay, and we're going to divide by that same thing. X plus 16 plus the square root of x plus 25. Okay, and this looks like, well, the numerator becomes x plus 16 minus, I haven't taken a limit yet, so I should write that in there, minus x plus 25. But the denominator looks like the square root of x plus 16 plus the square root of x plus 25. Okay, and so that numerator, the x's cancel, right? I get 41, and I've still got this denominator x plus 16 under a square root plus the square root of x plus 25 under the square root. Okay, the denominator, that gets really, really big, right? These guys go towards infinity, so this thing is going to go to 0. They're going to get close together after I rationalize that expression. Okay, that's it for 2.6. We've done a lot of limit stuff, and that's the end of the chapter as well. So we're going to wrap this up, and we'll see you in the next chapter.